Resolving power of a telescope. Suppose we are observing two nearby stars with the help of a telescope. Here only the limited parts of the wavefronts of light coming from both the stars pass through the lens and make an angle alpha at the lens of the telescope. Hence the diffraction will be produced, but clear point-like images of the stars will not be formed by the telescope. In fact, in the image of a star, there is a bright circular spot at the center, which is surrounded by weak rings. The central spot is the central maximum, and the rings are the secondary maxima. It is obvious that if angle alpha is large, the diffraction pattern will be quite distinct. Hence, the images of the stars, and thereby the stars themselves, will be seen as separate. But if the two stars are quite close to each other, angle alpha will be very small, and the diffraction pattern of both the stars will be so close that they mingle with each other. In this situation, both the stars cannot be seen as separate, and we find the image of only one star. The criterion for what should be the minimum value of alpha to get the distinct and separate images of the two stars was given by Rayleigh. The images of the two point-like objects can be seen as separate if the central maximum in the diffraction pattern of one falls either on the first minimum in the diffraction pattern of the other, or it is at a greater separation. The three situations, that is, when the images are quite separate, when they are just separate, and when they overlap, are shown here. If the diameter of the telescope's objective lens is d and its focal length is f, then the width of central maximum alpha is f times 1.22 lambda over d, where lambda is the wavelength of the incident light. Therefore, the necessary minimum angle to see the two images distinctly is alpha. This alpha minimum is described as the angular resolution of the telescope, and inverse of alpha minimum is known as the resolving power of the telescope.